All right, well, thank you very much for having me here speaking. And I'd first like to talk about so I'm going to talk about a single study today, almost two studies, so to try and sort of relax towards the end of the day. And I'd also really like to highlight this is very much a group effort and the product of collaborating with this fantastic team of people. I'd also really like to give my sincere thanks to NIH and NSF. So I did not think in 2025 we would be at the situation where maybe they wouldn't be around anymore. But so really happy that we still have them and hope they will be able to continue into the future. And finally, I'd like to really thank the organizers of the conference because it's been absolutely fantastic so far. So thank you. Right, so on to the topic at hand. So many animals, including us, but also my beluga friends here, Julka and Kilu, who sadly I'm not going to be talking about today, must use sound to identify unknown events, beings, and objects, differentiate them from other things, and crucially, use that information to act and fulfill our goals. So that's been a topic of many of the talks today, and I'm going to continue doing it. So even the shortest auditory scene can contain many classes of information. So for instance, if I just hear a few footsteps at night when I walk out the door, I can make guesses about the walker's gender, their height, age, identity, proximity, their shoes, what surface they're walking on, whether they're in a hurry, or even whether they don't want to be heard. So all of these very valuable clues are contained quasi-simultaneously by the sound coming into my ears. But the disambiguating information for each is often preferentially conveyed along different auditory dimensions, such as, for instance, the spectral centroid or shape, the onset envelope, the relative duration, and so on, at least when we're lucky enough to get those nice segregations. So in order to use this information for a given task or decision, so here, whether I go out to greet my fabulous Italian shoe-wearing dinner guest or run inside and lock the door, I do live in London, after all, on Industrial Street, I must discover the presence of task or category relevant sound patterns within particular auditory dimensions, and then figure out what the regularity is within these patterns and where they might lie along that dimension. So where am I going to find that information? So this might enable me to proactively hone in on and then use that information in the signal that is diagnostic for making a decision. So is this a fashionable woman or a lurking lager lout like the ones that we had in London this past weekend? So this might be especially useful for task-relevant information conveyed through sound, in that unlike most visual scenes, and indeed most visual experiments, this sound information only exists for an instant and then disappears forever. So we really need to think about what's going to be useful because it's gone forever after. So more generally, what's actually happening mechanistically when we learn to rely on specific auditory dimensions to make categorical decisions? So like, is that a ba or a pa, or is that a short or tall man walking past me? So we know that relatively short-term category learning in vision and audition can drive changes in neural representations of categories. So we've seen that in multiple talks yesterday and today. But what's actually happening here? So if following a lot of cognitive theory, is it that we actually are learning to automatically attend to that category informative dimension, or perhaps to the informative subspace along that dimension? So if that's the case, then we should see that intensive and successful category learning that relies on particular acoustic dimensions should drive attentional gain to the most informative part of that dimension for a particular categorical decision. So we should hone in on that information and where it is in the sound signal. So further, we might see that patterns of neural activity associated with learned attentional gain of the type that I just talked about along an auditory dimension are similar to those that are evoked by explicit attention along that dimension. So we might also see that endogenous attention to the informative dimension for the highly trained task that we've made people do, even might carry over when the same listeners perform a task with those same sounds, but where that auditory dimension that they've learned is really important becomes uninformative. So coming back to my footsteps outside of my door, I might choose my next action based on auditory dimensions that are informative about the walker's size. Are they really big or really small? And not how fashionable their footwear is, although obviously very important, as you can tell. So to address these questions, we decided that we needed to move to outer space to encounter and categorize novel space aliens. So we first created a new multidimensional perceptual space made up of over 36,000 unique sound exemplars. The sound exemplars that we made and the categories that were formed are completely novel to listeners, as are the space alien identity and space alien size visual cues that we use. So the space alien sounds possess information in two simultaneous, non-overlapping frequency bands, with each band having highly similar and really complex acoustic information. Both bands were populated with 3 400 millisecond chirps, a little bit like the cute gerbil chirps, played one after another, and each of these varied to some degree in frequency contour. So each of the 4 alien identities people had to learn are conveyed by spectrotemporal patterns within one or the other of these frequency bands. So said another way, one of these bands includes 3 chirps that are diagnostic of alien identity, and the other band contains non-diagnostic distractor chirps. So for example, here, the high band is diagnostic. So red indicates that each of the 3 distinct chirps share an underlying acoustic regularity that identifies this particular green alien, which looks a little bit like a gross earwig, but we'll avoid that, talking about that. So in this example, the low band is non-diagnostic of the auditory category. So here, simultaneously aligned chirps are also equally acoustically variable, but they don't have an underlying regularity across the chirps. So this is symbolized here by the 3 distinct colors indicating the 3 distinct chirps. So these chirps can come from any of the 4 patterns. Okay, so another alien in this group was also identified by a chirp pattern that regularity present in the high band, which is here schematized in yellow. So category learning thus depended on discovering the acoustic regularities shared by category consistent chirps within a specific frequency band and associating those band-specific regularities with a particular alien identity. So 2 of the alien categories had diagnostic information in the high frequency band, and the other 2 had them in the low frequency band. So why did we do this? It's probably quite obvious from listening to the rest of the talks and from your intuition. So we designed these stimuli specifically to take advantage of the relative spectral selectivity and mosaic tonotopy of much of auditory cortex. So this way, alien identity information in the higher and lower spectral bands will be preferentially processed in roughly spatially segregated clusters that respond to one or more of the spectral bands. So the very same sounds also provided category information about alien size. So whether or not that they were a big or small alien was conveyed through overall amplitude, which varied continuously across these alien exemplars, with the boundary between large and small aliens being pretty much in the middle of the amplitude range. Okay, so as many people know, when they've been doing experiments, it seems really great that it's like, oh, let's design some new stimuli, but often they don't really work the way that you did. So Chisamo Bassi, when she was doing her PhD at Carnegie Mellon, ran a lot of experiments to make sure that people could actually learn these alien identities in a reasonable amount of time, and also find out whether different training regimes might have an impact on learning. So the answer to the first question was yes, but they're in fact hard, and there's a lot of individual variability. And the second was actually quite surprisingly no. So I'd recommend this paper that Chisholm did an amazing job on if you're thinking about like how do I get people or non-human animals to actually learn something. So what we had read in the learning literature actually didn't really transfer so much to this more complicated category task. So after Chisholm did that experiment, in a really Herculean effort, Sahil Lutra and Rahat Razin ran 95 people through 5 days of online training on alien categorization. So participants were trained up on one of Chisholm's experiment conditions, where participants underwent a 2 alternative forced choice task, which, unbeknownst to subjects, was just blocked by a diagnostic band. So interestingly, as I alluded to, Chisholm didn't find this made learning any easier or harder than many of her other conditions. So participants also ended each day with training with a generalization, each day of training with a generalization task where they heard a bunch of novel exemplars they'd never been exposed to and then had to pick which one of the 4 aliens they heard. So then, even more heroically, Raha and Sahil enrolled the 49 participants who achieved at least 75% correct at the end of the 2AFC alien identity training into an fMRI study. As you can see here, I don't know if you can actually see my little, yes? Yeah, sort of. All these participants improved over time, some faster than others, and some slower, but all achieved excellent performance by the 5th day of training on both the identity and size tasks. So Raha also recruited another 20 participants for fMRI who only trained on the alien task, which, just as a reminder, didn't have any category information conveyed by spectral differences, just by amplitude differences. So this alien size trained group is really important for identifying any bottom-up salience differences that might differentiate sounds from specific alien identity categories regardless of category experience. So then in the scanner, the group that trained up on both alien identity and size performed blocks of the same 2FC identity and size tasks they did on training. And then the group that only did alien size just did the alien size task, as well as some other tasks. So after the main alien task runs, all only the identity participants performed a really demanding selective attention task where they were told to attend to one of 2 simultaneously presented tone streams that occupied the same spectral bands as the high and low diagnostic alien categories. So in previous research, several investigators like Lars Rieke, Sandra de Coster, I think is not here, Federico de Martino, and as well as us, have found that auditory cortical voxels and regions that respond to a particular frequency also show that you can discover this preferential tuning simply when you pay attention to that favorite frequency band of a voxel in a full spectrum sound, versus not paying attention to a less frequency band. So you can recapitulate really all tonotopic maps simply by paying attention across frequencies. So finally, both the main identity and size train group and the alien size train only group underwent a standard tonotopic mapping that we used to quantify each auditory voxel's preference for sound in high and low spectral regions that contained the category information about alien identity. Okay, so how do we actually test a hypothesis that successful learning of these alien identity categories will drive attentional gain to the specific category diagnostic frequency band? So we do this by combining the data from tonotopy and the categorization task to construct what we call concordance maps. So these allow us to capture consistent regional variation in responses across participants while retaining frequency selectivity at a voxel-wise level despite the tonotopic map inter-individual variability. So we want to really see where do we actually see auditory cortex responding to potentially these changes in attentional gain, but taking into account all of this individual variability in tonotopic maps that we've seen actually across the conference today. Okay, so how do we do this? So here, each individual's auditory responsive cortex is parcellated into a small set of ROIs defined across the cortical surface. So here, each ROI, or what we call ROIs, because they're very small, that exhibit frequency selective tuning at the group level, sample it on the cortical ribbon in each individual's native volumetric EPI space. So then we calculate the voxel-wise high minus low frequency band selectivity contrasts from activation in the tonotopic runs, and the analogous voxel-wise contrast of activation for aliens whose identity is disambiguated by information in high and low frequency category diagnostic bands. So these parallel difference scores then let us fit a regression model across all participants within each ROI. So this reveals the concordance within each ROI between the voxel-wise frequency selectivity and our hypothesized category-specific frequency band selectivity that's driven by the alien identity training, but not by the alien size training, or at least this is the hypothesis. So to put it a different way, this approach allows us to ask whether or not categorization decisions that are guided by chirp patterns that are embedded within high or low frequency bands yield differential activation in corresponding frequency selective cortical regions. So since each category exemplar has a lot of acoustic energy in each frequency band, as well as substantial amplitude variation that signals alien size, we can take an exaggerated neural response in the identity diagnostic versus non-diagnostic frequency band as evidence for expertise-driven changes in cortical activation to the category exemplars. So in other words, we expect to see changes in intentional gain really changing, at least transiently, the underlying frequency preference in a higher level dimension. So if intensive training on alien identities does actually result in a shift in endogenous attentional gain to the category diagnostic spectral region, then we should also observe this not only when identity-trained participants perform the identity task, so which alien is it, but also when they perform the identity size task, which relies on amplitude-based categorization. So this is basically, do we see a generalization across contexts of this attentional gain that becomes kind of like a learned salience of these new diagnostic spectral regions? So, after all of this, what did we actually find? So first, to what happens with all alien identity expert participants who are actively performing the alien identity main categorization task. So what we see here is that in multiple auditory ROIs, that there is greater cortical activation associated with the category diagnostic versus non-diagnostic regions that was predicted by the same voxels stimulus-driven preferences for one or the other frequency band. So these white outlines are showing ROIs that are significantly related when p-values are FDR corrected, because there are a lot of ROIs here. So what we see is that left hemisphere auditory cortical ROIs along this really most of the swath of the plantar temporale, so moving forward from Heschel's gyrus as featured by Tyler, posteriorly to the anterior-most aspect of the tonotopically mapped temporal lobe, we saw that there was a strong positive correlation, causative correspondence between the category diagnostic versus stimulus-evoked voxel-wise frequency selectivity. I need a drink of water here. There are too many S's in my talk. So we also see more posteriorly that some of the left posterior ROIs along the STG also show this positive correspondence. So in the right hemisphere, we observe a significant positive cross-task correspondence in multiple clusters of ROIs here. I should also note that there are these few ROIs with a negative correspondence. These tend to be in areas that across participants show very, very kind of sketchy and weak group-wise tonotopic selectivity. So now what happens? Are we going to see generalization when these same expert participants make alien size judgments that are based on amplitude? So we predicted that alien identity learning will cause identity diagnostic spectral dimensions to acquire salience, such that the frequency selective recruitment might occur even when those task demands shift to just using amplitude to characterize, but yet they can't actually ignore that newly diagnostic spectral information. So indeed, we see that there is actually preferential for the identity diagnostic information even when it's task irrelevant. So in the left hemisphere, we observe significant concordance between most of the ROIs in the planum temporale, as well as two in the posterior part. And then there's a little bit less concordance in the right hemisphere, but it is quite noticeable nonetheless. Moreover, we also see that there is, actually that I'm not even showing here, we see that there is significant concordance between those two maps. So, when don't we see this? So what happens when we look at that alien size group who has only trained on alien size and has never trained on alien identity? Here, only a few ROIs show selective concordance, and again, they were in these kind of peripheral regions. So you see that sort of blank here on those size trained participants. So then, when we look at directly comparing an n-matched sample of identity experts to the alien size experts, we see that this change is very big. So all of those red regions show ROIs where there is much greater spectral selectivity for those alien identity category spectral dimensions compared to the ones that were just shown by, that only relied on size during training. So this result strongly suggests that the differential cortical activation to the identity diagnostic band is not just due to this bottom-up salience that we might expect. So instead, it's more consistent with a kind of acquired salience for the category diagnostic dimensions that are related to learn endogenous attentional gain to the diagnostic region for each identity category. So, coming back to our hypothesis about the kind of underlying mechanism, we might then see that the voxel-wise preferences of differential activation to high versus low frequency diagnostic band correspond with the analogous contrast of explicit attention to those two bands within a tone stream task that we torture people with. First, we made sure that the attention toner-topy task actually worked. Indeed, what we're showing here is the concordant match between the two. So we see that across the board in right left hemispheres, that much of auditory cortex shows strong concordance between the two maps. We see in the left hemisphere that most of these left auditory cortex voxels, except in the anterior, lateral, and posterior STG, are showing concordance. And then in the right hemisphere, spectrally directed attention evokes similar activation differences as tonotopic scans along the lateral planum temporale again. And so this is really just replicating work from Lars, Federico, Sandra, and us. So what happens when we actually ask whether or not patterns of cortical activation that are elicited by explicit directed attention to the frequency band align with activation patterns in the same subjects that arise in category decisions that are implicitly reliant on information in those same frequency bands? So these cross-task concordant maps that you're seeing up here showed that analogous differences in activation to high versus low frequency bands that are observed laterally in both hemispheres in a swath of ROIs across the central part of the STG and abutting as well ROIs in the planum temporale. So I should point out that this relationship holds even though these stimuli are really, really different. So in one task you have really this like broadband spectrum, and the other you have these kind of like funny little stimuli that are used for the explicit attention task. So we also, when we split up people into how they learned, So we actually see that the trajectory of learning itself leaves fingerprints on the cortical response to category experts in the fMRI task. So we grouped people into people who had learned really fast, so early experts, and you can see here that they learn really fast, so that like out of the gate after the first day of training, they're extremely accurate and keep being accurate and are presumably consolidating their knowledge about these categories. Late experts, on the other hand, started out okay, but then they really made a lot of strides. And by the end of training on day 5, they got as good as those early experts, and they were just as good in the scanner as well. So if we just looked at performance in the scanner, they're absolutely behaviorally matched. Nonetheless, when we look at the maps of these people doing exactly the same task, we can see that there are these fingerprints of the trajectories of learning in the cortical response to category exemplars. So compared to late experts, the early experts show stronger concordance between the alien identity categorization and stimulus-driven voxel-wise preferences in almost all of the lateral anterior ROIs in the left hemisphere, and particularly the anterior-most part. So in the right hemisphere, we see that early experts show greater concordance in ROIs along much of the crown of STG, and somewhat less concordance medially compared to the early experts. And so I should really point out that these people are all experts. This is a really, really hard task, which unfortunately I can't let you hear because PowerPoint does not allow me to. So the performance, again, is excellent, but yet it's that history of training and history of learning and figuring out how these categories are structured that we still see evidenced in these maps. So what have we actually learned from the results? So first, we see that active engagement and sustained category learning drives changes in neural representations where there's increased gain for the category diagnostic information. So previous studies in both humans and non-humans have seen such changes that are related to category decisions a lot in frontal region. This is true in both visual and auditory category learning, but rarely do you see it in sensory cortex itself, and certainly not to this degree. So what's more, the learning-driven increased gain to the information channel that contains that category information persists, such that even when we change the category task to one where you do not use that information, in fact, it's not good for you to use that information, people cannot let that go. So we keep seeing that increased gain in experts on the category identity task, even when they're doing something completely different. And so this is reminiscent of the kind of learned salience that's been observed for information channels or diagnostic dimensions in other domains. So just as an example, Adam Tierney has seen this in a number of studies that he's done with Mandarin speakers who really prioritize pitch contours. And in fact, when you use pitch contours in other contexts, they have problems disengaging from this pitch information when it's not even relevant to the task. So suggesting that pitch contour as a kind of dimension increases its salience for people whose language relies on that cue. So this data also connects a lot with non-human animal electrophysiological studies, including the ones that we've seen today, that observed that the task relevance in an acoustic dimension really drives change in the receptive fields consistent with attentional gain. Obviously, Jonathan and Shihab really started this out along with Stephen David. So we also see that the learning-driven and spectrally specific modulation of activation to exemplars of each alien identity category is very similar to what you see when you direct attention explicitly to those same bands. So this is in line, but not knockout, drag-out evidence for this theoretical idea that what we see occurring is that there's an increase in attentional gain to these diagnostic features. So finally, we see that there's this echo of learning trajectory on these patterns of activation. So even though all of our subjects learn really, really well, we see that the degree to which they have consolidated the information across days of training is still seen in patterns of activation. And this is quite reminiscent of a number of studies in development, where you see even indeed back to Brad Schlager's work, where you see that kids of different ages, even though they're performing very, very similar on difficult tasks, seem to do things very, very differently. And that you see this kind of growing up and growing down of regions across development that's associated with expertise. Right. I think we are ready to go.
That's right.
Thank you very much.
Thank you, Fred. We have time for one quick question, including why the heck is that on the screen? It counts.
Hi, great talk, Fred. How persistent do you think these effects would be? If you were to rescan or retest these individuals in, say, a year, would you expect to see these types of functional activation shifts even after that amount of time?
It's an excellent question. So we do, these are a little bit after they've scanned, but I seem to have lost the ability to do these, as I was finding as I went over the stimuli, but I think you would still see some degree of attentional gain, and that it would come back. Basically, you would see it really fast. So a little bit of kind of.
Since you're the next
yes.
speaker, we'll give you privilege.
Yes.
Just a quick question. If
Yeah.
you try to do something to break the attention, so do something like articular suppression or something that says that they retain an implicit ability to do this.
Well, so an excellent question. I think we need to get at this behaviorally. So ideally what we would do is show that there's a kind of behavioral signal of attention, such that, for instance, people would be better at detecting some sort of relevant tone within the diagnostic band.
Idea.
Right.
Break the
Okay, we're going to let those two
Okay.
debate it out.
So, yes.
We got a half an hour